Hi everyone. For the coming week, we are going to explore more into the semantics of programming languages, which will be the fundamental of our course. So today, first, I'm going to introduce the general concept of programming language semantics, and then especially cover one particular style of programming language semantic formalization called operational semantics. Okay, let's get started. Let me first talk about the essence of programming languages. So, what does a programming language consist of? Let's think about this. When you want to design a programming language, what would you do? A bit more concretely, if you want to implement an interpreter, compiler, or program analyzer for a certain programming language, what would you do? Okay, there are so many programming languages out there. So what is the principle of programming language design for such languages? So as you can guess, there are two important things. One is syntax and the other one is semantics. Okay, the syntax defines the grammatical structure of programs, which means that syntax determines the textual shape of programs in a certain programming language. So analyzing such a grammatical correctness is so-called parsing. So parsers check the syntactic correctness of program and produce a byproduct called abstract syntax tree. Okay. For example, a parser takes this one-dimensional character string and check whether it is grammatically correct or not, and then finally it produces this two-dimensional abstract syntax tree. Okay, I assume that you have already learned about parsing in undergrad courses, so I'm not going to get into the details of parsing this course. So here is a grammar for a simple imperative language we will consider throughout this lecture. So it looks like a C programming language, but it is much more simplified version. Okay. Okay, then let's take a look at how programs look like and what this notation means. The first category is represent a set of arithmetic expressions. So we will use this meta variable e for element of arithmetic expression. So each arithmetic expression is one of the followings. It can be integer constant or a variable or a binary operation like this. This can be any standard mathematical binary operation like plus, minus, multiplication, and division. Okay. The second category is a set of Boolean expression. There are Boolean constants like true and false, and also standard comparison expression like equivalent or not equivalent, and less than, and so on. So finally, the last category is the set of commands. Okay, so a command of this programming language is one of the followings. Skip, that does not do anything, and sequence of two commands, and each subcomponent is also a command, as you can see. So see, this is an inductive definition. Okay, so another one is assignment. So the left hand side is always a single variable here, but the right hand side is an expression defined here. Okay, so the next one is input command that reads a value from outside and store the value to this variable. Okay, the next one is conditional branch with a single Boolean expression and two subcommands, and the last one is a while loop with a single Boolean and a single command. So okay, now we understand the syntax of this program, and the parser will automatically check this grammar. But understanding syntax, which means understanding grammatical correctness of a program, is not enough to estimate the behavior of the program. Okay, I guess all of you can write C programs, but do you really think you fully understand the C program's behavior? Okay, here are some small quiz to check this question. So first, here is a simple C program. So the question is, what would be the return value of this main? Okay. Here is a simple structure definition, and we know how size of expression work here. Okay. Then what is your answer? So keep the answer in your mind for a while. And let's see the next example. So here is another small C program, and still, can you guess the return value of this main function? There's one variable a with a type of character, and the other variable b with a type of short integer. If you compare these two expression, what would be the result? Can you guess the result? The last example is a bit traditional one. So here is a variable I and two increment expression. So pre-increment and post-increment expression. So what would be the sum of them? What is the return value of the main function? So here we have observed three examples. So what are your answers? So if you read my intention, and you would have this correct answer like this. So for all questions, the answers are actually I don't know, because according to the C standard semantic definition, all the behaviors here are unspecified and can be different depending on compilers or architectures. Okay, but I'm not going into the details of this example more. So if you want to understand the reason more, visit this website here. Okay, but here my point is that it is very important to understand the formal definition of programming language semantics when we write a program manipulation or understanding tool like interpreter or compiler or analyzer. So the question is, how is the semantics of each statement and expression of a program defined formally, and what are the statements whose semantics is unspecified? So these kinds of questions are really important to understand the behavior of a program correctly. Here is a funny video that shows the importance of formal and clear semantic definition of a programming language. So from now on, our main interest is semantics. So semantics of programming language concerns with the meaning of grammatically correct programs, so that interpreter execute programs with respect to the semantics. Compilers translate source programs with respect to the semantics and generate target programs. And analyzers, which are the main interest of this course, analyze programs' behavior with respect to the semantics. Okay. Once we understand the semantics, we can answer this kind of question. So this is one example. Are these two programs equivalent? If so, why is that? So intuitively, we can answer this question because we know that variable names are not very important to determine program's behavior. Okay, so the answer is yes, they are equivalent. Another example is here. So the question is this program transformation, which is actually program optimization, correct? So if so, what is the reason? So again, we can answer this question because we know that this statement does not contribute to generate the output of this program. So this optimization is correct from the compiler's perspective. Okay, so all such kinds of non-trivial questions can be answered only when we clearly understand the semantics of the target language. Okay, so let me talk about how the semantics of a program can be formally specified. So there are different styles of defining semantics of programming languages. One is so-called operational semantics, also known as transitional style. So as you can guess from its name, operational semantics focuses on how to compute the execution result. For example, here is a simple program of numerical expression. What is the meaning of this program? So according to operational semantics, the meaning of this program is a sequence of transition or a sequence of operations of the target machine. So for this particular example, the operational semantics of this program is defined as a sequence like this. From the original expression, okay, the machine operation leads to the intermediate expression 3 times 3, and then finally the machine state reaches the final expression, which is 9, and then the machine finally halts. This is the description using operational semantics. Okay. Another style of formalization is called denotational semantics, which has a slightly different perspective of programs. Here we focus on what the ultimate execution result is rather than the operation or transition of machine state. So with the same example, this style of semantics does not care of how the expression is computed, but only take care of the ultimate result, which is 9. That is the meaning of this program using denotational semantics. Okay, but notice that to get the final outcome of this whole expression, we have to know the final outcome of all the sub-expression like this. Okay, so this semantics of a program or an expression is compositionally constructed using the semantics of the sub-components. Okay, so in that sense, this denotational semantics is so-called compositional style. So also there are more types of defining programming language semantics for different purpose and different characteristics of languages. But in this lecture, we will only cover 2 representative styles, which are operational and denotational semantics.